Okay, Jasmine, I'll try and do this before the girls wake. Might have to do it in a few goes, but here we go. So this equation here is what you'll be using. N equals mass divided by molar mass. So number of moles. This simply is a convenient way to talk about how many particles of something there are in a chemical reaction. So 1 mole of anything, any substance at all, is 6.02 times 10 to the 23. Now that's a crazy number, and doing any sort of problem would be ridiculous. So we simplify it as being 1 mole equals 6.02 times 10 to the 23. We don't even really need to worry about it because in chemistry, any chemical reaction is balanced in terms of it's got a balanced equation. There's the same ratio of each thing. And therefore, because of that, we can relate the number of moles. And I'll explain that a bit more as we go through. So mass is in grams, and molar mass is simply the mass of the individual elements that make up the compound. So a bit more on that. So the mass of 1 mole of substance is exactly equal to the substance's relative atomic masses in grams. So basically what that means, if we've got the molar mass of ammonia, NH3, that's just adding up the relative atomic mass of nitrogen and 3 hydrogens, and that gives us the molar mass 17.04 grams per mole. Okay, so hopefully that makes sense. So relative molar mass or molar mass is simply the mass of the individual elements together, and that mass is the mass of those elements, of 1 mole of those elements. So if you look here, to put it into a calculation to make that make more sense, if I said to you calculate 1 mole of sodium hydroxide, then 1 mole would be, you would first of all, we're using this equation here. Okay, so I've asked for 1 mole, so N would be 1. Okay, I've asked you for the mass, so we're solving for that. So that one there's the X, and then this one here is the molar mass that we can always find, because on your periodic table is the relative molar mass of every single element, and so therefore if we look up sodium, it's 22.99, oxygen 16, and hydrogen 1.01. So if you add that up, that's 40 grams per mole. So that's the molar mass. So if we then calculate the mass, okay, this being 1, this being 40, then it's 40 grams. So molar mass is the same as the mass of 1 mole, essentially, to try and make that relationship make sense. So mass is the same as molar mass for 1 mole. I hope that kind of makes sense. And you can do all sorts of equations or calculations using this relationship, N equals mass over molar mass. So another one here is, what if I had 10 grams of sodium hydroxide? What's the number of moles? And so you just do 10 divided by 40, which we calculated the molar mass was 40 earlier, and that gives you the number of moles. So number of moles, that's just a specific number here. What we're going to do now is talk about limiting reagent and then link that to an equation. Hopefully it'll make a bit more sense. I'm working a bit backwards here and kind of condensing things, because you can see here this is slide 132, and so the previous 132 would be me teaching about the mole in far more detail than I have time for. So limiting reagent, pretty much you'll know that any reaction's got 2 or more reactants. Well, actually it's not true, some reactants just have 1, but for simplicity's sake, let's say we've got 2 reactants for a reaction. Those 2 reactants add together to form a product. If one of those reactants runs out, then the whole reaction stops logically. And so whichever one of those reactants that run out, that is the limiting reagent, okay? The other one, the one that there's still some of, is therefore the reactant that's in excess, okay? So the reason why we use limiting reagents is because the one that runs out effectively determines how much of the product we can make, and we can use that knowledge to work out the theoretical yield we'll get, and that simply means the amount of product we can get. So we're going to be looking at this problem here, and I'm only going to show you method A. It's the one that I tend to use all the time, but there's multiple ways of doing this because there's multiple ways of doing these equations. So I've broken it down. So method A, here's the equation that we're talking about here. Now you probably aren't familiar with all of the names of these. That's something that actually every student finds really hard, but you'll pick up on a few as I go through them. That's just a completely different skill. So here we've got 2 ammonias reacting with 3 copper oxides to form nitrogen, copper elemental, and water. Now the key thing here is the numbers in front of these compounds. So we have got a 2, a 3, this is 1, if there's nothing it's a 1, 3, and 3. So what that actually means is that's actually the molar ratio of these compounds when they react. So 2 ammonias react with 3 copper oxides to produce 1 nitrogen, 3 copper, and 3 waters. So that's the molar ratio, and that's really, really important. The next thing is, here's the information that you've been given. It says if you've got 18.1 grams of ammonia and it's reacted with 90.40 grams of copper oxide, determine the limiting reagent and the mass of N2 that can be produced. So first thing in chemistry, and where students always go wrong, is they think that you can relate masses, which you never can. Okay, so anytime you're given a mass in chemistry, you must always turn it into a number of moles. And so you've got a mass of ammonia here. Okay, you can straight away turn that into a number of moles by doing N equals, this is hard to do because I've only got my keypad, sorry, mass over molar mass, but it's typed out on the next slide. So N equals mass divided by molar mass to work out that number of moles. And you can always know the molar mass because you've always got access to a periodic table. And remember, that's what we were talking about before. That's adding up the masses of 1 mole of each of the elements in that compound. So that's step 1 of any problem. You always turn something into a number of moles, and you can relate the number of moles. Now, I've chosen this example because it's quite hard. It's got all different molar ratios that you're going to have to compare. So let's go through to the next step. Okay, so from here, you then have to work out those number of moles, like I said. So I'm just trying to find my cursor. There we go. So the number of moles of ammonia, the mass given divided by the molar mass. So you add up 14 from nitrogen and the 3 hydrogens gives you 17. And then you do the number of moles of copper oxide, and you get these 2 number of moles. So what do we do now? We've got a number of moles, but we still haven't been able to link that back to this equation where you've got these ratios. Now, these ratios are super important because that's the molar ratio of the reaction. So we're concerned with these 2 compounds, NH3 and copper oxide. So you've got 2 NH3 for every 3 copper oxides. So that means that to relate these number of moles, the easiest way is to divide your NH3 by 2, because that's how many numbers of moles, and your copper oxide by 3. And then what we can do now is we can plug in using these numbers of moles that we just calculated. I'm just trying to find my cursor. Very hard without my pen, sorry. We can use these number of moles that we've just calculated to work out which of these is the limiting reagent using these ratios. So pick either one you want. It just so happens that I'm going to calculate copper oxide. So whichever one you're trying to calculate, cover that one up. So I would cover that one up, okay, and that means that you need to get rid of that 3. So you times the 3 over the other side, okay, because we're solving for copper oxide. So if you times that 3 over the other side, 3 over 2 times the number of moles that we've solved for NH3, which is 1.062, and you get this number of moles. So that's saying that if we have 1.062 moles of NH3, we need 1.593 moles of copper oxide. Now, you can see, if we've got this many moles of NH3 and we need 1.593, well, you can see we don't. We've only got 1.136 moles, which means that copper oxide is the limiting reagent because we don't have enough. So I'm going to go through that again just to make sure it's made sense. So we've got these numbers of moles. This is factual. This is given from the question because we've converted the masses that were given to you using the molar masses we can always get from the periodic table, and we've got these 2 numbers of moles. Okay, so these are what we have. We can't change that. What we can do is we can use the molar ratio from the equation, which we always have to do, to incorporate the fact that for every 3 copper oxides you need 2 ammonias. So I've just arbitrarily chosen to solve for copper oxide, but you could have chosen to solve for ammonia. And I've even actually done that problem just here. So this is not needed. You only have to do one of these to work out the limiting reagent, but I've just done it to show a different way, like to show the other way. So cover up what you're trying to solve for. So I've scribbled out copper oxide because I'm trying to solve for it, and so you need to get rid of the 3 that's below it, so you times the 3 to the other side. So 3 over 2 times the number of moles of NH3. So we've got 1.062 moles of NH3, and so if we times that, you get 1.59 moles of copper oxide. So that's saying that if we've got 1.062 moles of NH3, you need 1.593 moles of copper oxide. But we don't have that. We've only got 1.136, which is less than that. So that tells us that copper oxide is our limiting reagent and NH3 is our reagent in excess. I hope that makes sense. I could have done it the other way. I could have solved for NH3, which means I would have times the 2 over the 3 here, and times by the number of moles of copper oxide, and you would have found out that if you had 1.136 moles of copper oxide, you needed 0.757 moles, but we have 1.062, which is heaps more, telling us that NH3 is in excess. So once you know what the limiting reagent is, that's the number that's going to determine everything else in the reaction, that number of moles. So this number of moles here, the limiting reagent, is going to affect everything else in this reaction, because once this is used up, the reaction can't happen. Okay, so once that number of moles is gone, you've just got NH3 left and the reaction can't happen. Now what you'll see here is you'll see that you've got 3 copper oxides for every 1 N2 that's produced. So what that means is if we've got this many moles of copper oxide, if we divide that by 3, we will find out how many moles of N2 are actually produced, because it's all ratio based. So if this is the amount of moles we've got of copper oxide, then 1/3 of that has to be the number of moles of N2. So we do that calculation, and down here you'll see the number of moles of N2 that's produced is 0.379. So therefore we know, because we've got the number of moles, you've always got the molar mass, you can then solve for the mass of N2 that would be produced in this reaction. And so this is the molar mass of N2, so N is 14.01, so 2 of them is 28.02. That gives you a theoretical yield of 10.7 grams. So that's essentially what limiting reagents are, is using molar ratios to work out which one's going to run out first, and the one that runs out determines how much of the products you can make, essentially. So we have to use that number of moles. So I hope that's made sense. Let me know if it doesn't. I'll quickly flick you through. This is an alternative way that you could have done it, so you can pause this video and have a look if you prefer this way of doing the calculation. And then here's another method you also could have done. Also, just to add to your kind of understanding, here's a little task I wrote for my kids in class. So what's the theoretical yield using this equation here? And here's the answer. So you can have a look at that. And then I've done another task, and you can pause the video, and here's the answer. Okay. The final thing with limiting reagents is in theoretical yields is you can use theoretical yields to compare to experimental yields, and I'm not sure if you need that or not, but it's really easy. So if you've got an experimental yield, you can divide it. Experimental is just what you got from an experiment. So we did the experiment from the before and we got 7.8, but we know we should have got 10.2. You can see how successful your experiment was. So we had a 76% yield, not terrible at all, but it's not 100%. So this is really important in drug manufacturing. So I hope this has made sense and been a little bit helpful. You can let me know. Yeah. See ya.